Hello, good morning, good evening, good afternoon, everybody, wherever you might be. It is my great pleasure to introduce Walter van SUIJLEKOM from Nijmegen, and he will tell us everything and more about his generalization of K-theory to operator systems. It's all yours, Walter. Take it away.
All right, thanks very much. Thanks for the invitation also. So please let me know if you cannot hear me or cannot see anything, but I think it should be fine. Yeah, so what I wanted to end up with is something I've been working on recently, which is on K-theory for operator systems. So generalizing it from C-star algebras to operator systems. And that's motivated by several things I've been working on, and I'd like to start with that. So let's start with a little motivation. So the idea, and this is of course an idea in non-commutative geometry in the sense of Alain Kohn, which is well known but still good to sort of to reconsider, is that if you look at the way we describe geometric spaces, there's some notion of metric, and then usually the notion of a distance between 2 points. You get it from, say, putting little arcs and measure the length and take the smallest of those and compute that using the metric. And that's giving you some kind of notion of a distance between 2 points. Now, if you want to translate this more in terms of function algebras or actually more generally C-star algebras, you have to sort of dualize this definition. And actually what you can do is the following. You could also take the largest of differences in function values, where you take, well, this picture sort of illustrates it, where you, instead of taking the smallest distance between x and y, what you actually do is you take f of x minus f of y, their difference, and you take the largest of those for functions with the gradient smaller or equal to 1. And then you get the same function, and in fact, you can show that this can be nicely captured, this distance between 2 points, as the supremum over those functions with this gradient condition. And then evaluation states actually at x and at y, and you take their difference. And the gradient is governed by something which is, it's a very nice device called the Dirac operator, which exists on some manifolds. But one could actually work with Riemannian manifolds in this context, where you take a Dirac operator that is a first order differential operator, but it captures the derivatives in all directions at the same time. So if you look at the norm of this commutator that I depicted here, you'll find that it's actually the gradient of the function f. So it measures the sort of the gradient, the derivatives in all directions at the same time. Now that's actually the key to showing that if you take functions, so smooth functions, for say, and you take them to act on some Hilbert space, on which also you have a Dirac type operator acting, then you can, with this formula, at least reconstruct the metric of this geometry. And that's this sort of the key, one of the steps in generalizing Riemannian geometry to non-commutative spaces. So in fact, what you find is that if you do this more generally, and this is the basic sort of package that we consider, if you take a star algebra, let's take it to be unitall, of bounded operators acting on some Hilbert space H, together with this additional operator D, but now it's completely abstract. It's a self-adjoint operator with compact resolvent, and that sort of captures the fact that it came from an elliptic differential operator, which is also symmetric, on a, say, closed manifold. And then you have this first order property being a first order differential operators translated as being bounded commutators, which is of course very useful in this formula I just showed you. And so they gather in this Hilbert space as operators on this Hilbert space H, where the algebra is indeed bounded, as I said, and the Dirac operator is typically, or the generalized operator D, is typically unbounded. But still, with this same formula, you can introduce a distance, and now you sort of dualize the situation where previously I was looking at points and taking functions. Actually, I got the distance by looking at states, certain states. In that case, they were evaluation maps. Now that I can do here as well, in general. So you can look at states as positive linear functionals, and you get a distance function from this spectral triple that I have, and you get a distance on state space. And one could restrict to pure states if you wish, but that's sort of the key to at least get some notion of geometry from this general context of a spectral triple. And I would like to note here already is that if you want to look at, so what is the more general context in which you can do this, then you find that states, they're positive linear functionals. It doesn't really need a multiplication in the algebra A. It's just a positive map, which has a certain norm property, namely norm being equal to 1. So that can actually be done also on a so-called operator system, which is defined in this concrete situation as a self-adjoint vector space consisting of bounded operators. So it's closed under the star, and one may also desire to be closed as a subspace, but that's not necessary. So that's just a point to make, which we'll of course exploit in a moment. All right.
Sorry, Walter, let me
Yeah, go
ask
ahead.
you some very simple-minded questions. So did I understand you correctly that you can have the supremum just over the pure states and it'll be the same supremum as if taken over all states?
No, I don't take the supreme over states. The supreme is over elements in the algebra.
Oh,
And
I'm sorry. Oh, yes,
I get a
you are right. Of
distance,
course. Sorry. Yes, you're right.
distance
And
between states.
satisfying this. Yeah, yeah. My bad. Sorry.
But in
Of
particular, you
course.
get a distance on the extreme boundary, so on the pure states. Yeah.
Mhm. And could you, since I already, interrupted you, could you remind us how this concept of a distance is related to the concept of a distance like the metric geometry, but without manifolds, refill style?
Yeah. So there's of course an amusing fact now. Maybe that's a good point to make here. So you get this distance function on the state space, but
Hmm.
um, uh, or you already have a topology on the state space. It's the weak
Right.
star topology. So you may
Exactly.
wonder, so when does this metric that I have over here on state
Hmm.
space, when does it metrize that topology? And that's the key actually in the notion of quantum metric spaces of Mark-Rietveld. And then
Hmm.
it's even slightly more general where you don't take just commutators with Dirac operators and then or with operators D and then take the norm, but you take so-called Lipschitz seminorms. And that's actually the place where you find this compatibility between the topology and this
Hmm.
and this metric, and then you call that a quantum metric space. Yeah.
Yeah, thank you very much. Yes.
And not just for algebra. So again, that's actually written in the context
Aha.
already by Mark for all the unit spaces. So already modeling a little bit, or it's kind of a prelude to these operator systems.
Hmm.
All right. Thanks for the questions. Um, so so one thing I wanted to kind of reflect back on is that so what do you actually need is that it's quite a lot in a sense. And if you think about so this is spectral data we need. So you need this whole Dirac operator. And if you think about eigenvalues, maybe written out in an eigen basis, then you need all this information. And that's if you think about physics, that may not be very realistic. So that's sort of my motivation from during the last few years. You may wonder, so can you actually describe geometry at a certain energy scale? So when you are having this data available only up to a certain energy scale or energy cutoff, or with some resolution that's maybe spatial, then you may wonder, what do you actually describe if you take only part of that data? And actually the same motivation comes from if you do computer simulations, because they have to be finite dimensional. So somehow you would like to do spectral geometry on a computer, but so you have to implement it in finite dimensions. And then we also have some evidence that you can actually do that in an effective way. So there's been work, I think I have some references in a moment. But for instance, Barrett and Glaser, they worked on computer simulations, Monte Carlo simulations for spectral geometry, and also others, James Gaunt, worked on these fuzzy tori. So that's a place where you can do spectral geometry and you actually find some non-trivial output. And what you even find is that you can do index computations. Even though you're in finite dimensions, you can somehow still capture an infinite dimensional or Fredholm index. And that's by use of the spectral localizer. Also in a context where you try to simulate, that's in that case condensed matter systems, but on a computer. And then you find in the work of Loring, Schulz-Baldes, and many others that the spectral localizer, which is a finite dimensional object, actually captures the infinite dimensional index. So somehow there's this data available, and I would like to describe today how we can actually capture that finite dimensional data. So that's what I'm saying. So I'd like to describe that. There's been previous work. I mentioned already Glaser, also together with Stern. In my group, they worked on spectral geometry on a computer. And the previous works are with Alain Kohn and myself. And yeah, maybe the earlier work of Francesco, Andrea, Fedele Lizzi, and Peri Martinetti, that's already doing these spectral truncations that I'm about to explain. But what we do is we sort of extend this to sort of embrace these operator systems. All right. So if we were given this set of data, say a spectral triple, then the idea of taking only part of the spectrum is sort of realized mathematically by taking a spectral projection. So let's do that in finite dimensions for convenience, so we don't have to worry too much, even though it can be done more generally. But so you project onto a closed Hilbert subspace. So let's take finite dimensional Hilbert subspace. And of course, since it's a spectral projection for D, this capital P, what you get if you let D act on that Hilbert subspace, it just respects that. So it restricts to a self-adjoint operator there. All the properties still hold, bounded commutators and compact resolvent, of course, trivially because it's finite dimensional. However, this algebra, it does not act on that closed, this Hilbert subspace. That's because, so P is typically not in the algebra. So if you look at the compression of the algebra, so it's not a corner in the algebra, but it's a compression, then that's not an algebra anymore because it doesn't close under the product. However, and that's where these operator systems come in very conveniently, it is an operator system. So it does close under the star. And of course, there's also, it's a vector space of bounded operators. So the vector space structure is still there. There's this star, which is compatible. So it does appear as an operator system. Another incidence of where this happens is when you take spatial resolution into account. So take some finite resolution. And somehow in the metric space, you cannot distinguish 2 points, x and y, if their distance is smaller than epsilon. So what you want to do is to relate these points, so introduce a relation. And this is a so-called tolerance relation. So it's symmetric and reflexive, but not transitive, of course, because my epsilon is fixed. And then what you can do is look at in a sort of a groupoid style, look at integral operators that you associate that are supported on this tolerance relation. And that's somehow the underlying principle. Yes, Adam, I see your hand.
Yes. I have a question. Maybe it's a stupid one, but nevertheless, let me ask it. This operation, this truncation by the projection, is very standard in the context of von Neumann algebras. Do you think that there is some relevance of this fact in this context, or?
Well, I would say in that case, I'm not sure if that's what you have in mind, but then you take the projection in the von Neumann algebra. Is that the case? Is that what you have in mind?
Not necessarily. If you have a von Neumann algebra, you can take an arbitrary projection and then take multiply from the left by this projection and then restrict to the image of this projection, and this is again a von Neumann algebra, which is non-trivial, but okay, it can be proven.
Sure. No, that's very similar. Yeah. But let me see. You may then, how do you get the algebra structure? So you may want to generate it somehow?
I think that you have to prove something. It is not immediate, but it can be shown. And this new von Neumann algebra acts on the smaller Hilbert space, the image of this projection, PH.
I'm not sure how you can do
But
that.
everything is already represented on this Hilbert space H in this
Yeah, but
context.
so I'm saying, how do you get an algebraic structure if you take PAP and some PBP or something like this, it's not of the same form.
Mhm.
So it's not of the form P and then something P.
Um,
So I'm not sure what you have in mind. Maybe you take some kind of special type of projections or
no,
some.
the projection is quite general, but okay, this applying this P on the right-hand side is not done by multiplying by P, but you restrict. So this is not exactly the same, but this is somehow in the spirit. And I wonder whether it could be somehow helpful. This is something which is not natural in the context of a C-star algebras, but it is quite natural in the context of von Neumann algebras.
Mhm.
For example, it is how you define, for example, this abelian projections in this classification of von Neumann algebra. So an abelian projection is a projection P with the property that this algebra, such constructed in this way, is an abelian or commutative. And
Yeah, okay.
this
But
boils down to this type 1, for example.
yeah, sure. But don't you take the projection in the larger von Neumann algebra then?
Not necessarily. I
Yeah,
think that
sure.
the projection is general.
Okay. Well, we can maybe take a look at it or discuss it later. Thanks.
Okay, thank you.
Yeah.
Excuse me, I have a question about the projection D maps to PDP. After this projection, do we still have the bounded commutator property? Because before this projection, DA is a bounded operator. So after this projection, do we still have this bounded commutator?
And so what I said here was for convenience, I was looking at finite dimensional truncations.
Ah,
But
yeah, sure.
more generally, I would say so if P is I think it still holds because if P is a spectral projection,
Mhm,
actually the commutator of PDP with an element in the algebra, actually the P goes out of the commutator.
mhm.
So you actually compress the commutator, and compression is always that's a completely bounded map. So it will respect that as well in general. You
Yes.
see what I mean?
Yes, okay. Thank you.
Okay, thanks. Okay. So these are the sort of well, the point of these integral operators is that if you take products like convolution products of these integral operators, then that's again not closed. That may also be clear because the support will grow and not restrict to R epsilon necessarily. And so this is again something which, if you think about integral operators with that convolution product, or think about groupoid C-star algebras, in this case for the pair groupoid, then it will not form an algebra anymore, but it does form something which is closed under the star because this relation is symmetric. Okay, so that's say this the second motivation for doing this. So let's then look at these operator systems. Let's dwell a little bit into that direction. And there's a beautiful theory, and that was of course very nice, is that given this appearance of these operator system, we could actually use a lot of results that were already available in the literature. And so that was based on, first of all, the notion of an abstract operator system. So I already told you what a concrete operator system is. It's this set of vector space of operators which is closed under the star. However, like with C-star algebras, you can also have there's also an abstract version. And in the abstract version or definition of an operator system, the crucial structure is that of the ordering. So if I have bounded operators and I have some star operation on there, so I have a star closed vector space, self-adjoint vector space, then I can talk about positive operators in there. And that's this kind of cone is what is actually the starting point of the definition of the abstract operator system. So that's what it is. So we have a cone of positive elements, and then maybe not just at the level of E, at level of the vector space, but also at multiplication or amplifications. So you take matrices with entries in E. And if you take then self-adjoint of such matrices, and inside we have a cone of positive elements. So that's so-called matrix ordering. There's some notion of compatibility between these cones. So if you conjugate by some kind of rectangular matrix, then you end up in the other positive cone. So that's all quite standard for matrix ordering. The second ingredient for unital operator systems is that there is an order unit. So that's what I already referred to. This order unit space is actually the definition of just the level n is equal to 1 situation. So you have an order unit, which means that first of all, you can bound any Hermitian element between minus TE and TE. And so that's like with Caesar algebras. So you can always do that. And in fact, you can derive a norm from this by taking the smallest of such T. And then there's this notion of Archimedean order unit. If you can bound it from the left, say by minus TE, then it's actually positive. And again, that's something that you assume, and you assume it to hold for all these amplifications. So that's the definition of an abstract.
Sorry, can you remind me what this small h stands for?
Hermitian.
Hermitian, okay.
Yeah.
That's
So
what I
it's the
thought.
self-adjoint elements. Yeah, thanks. Yeah. And so within there you have this order unit and you have this ordering. So that's really the definition. And actually, so any such abstract operator system can be realized as a concrete operator system. And the realization is by means of maps that actually respect all of this structure, all this matrix order structure and so on. And so these maps are, first of all, completely positive. That means that they map positive cones to positive cones. And then the isomorphisms in this category are complete order isomorphisms. So bijections, and both the map and its inverse are complete positive maps. And such maps then arise in this realization of an abstract operator system in the sense of, so by making it concrete. And maybe a remark here is that if you think about C-star algebras, then that's a special case because we always have such an ordering. And then complete order isomorphisms are actually star isomorphisms. So that's also nice to sort of capture. And this was known in the 60s, 70s. So that's very nice to just take this information from that field. Okay, so let's well, not throw away all the things we know about C-star algebras, because that's, again, that's very useful, of course. And in fact, the link will be very relevant in what will follow. So there is some notion of a C-star algebra that you can associate to an operator system. And there are several, actually, but let's take the smallest of those in a certain sense. And this is due to Arveson, who was looking in the 60s at function spaces or function systems, and then think about what is actually the C-star algebra. It generates a set of functions on some space. What does it generate? And maybe is there a smallest such, let's say, C-star algebra being generated? Now, Arveson didn't manage to prove the existence of such a unique C-star envelope or C-star, C-star envelope. Uniqueness is actually from universal properties. But it was done by Hamana. And then later, it was actually brought back to the original plan of Arveson by, actually, interestingly, a sequence of Dirchan McCullough first and then Arveson again, and then two students, or a student and a grant student, to finish this line of thought in 2015. So I will mention both. So let's look at what I actually have in mind, what Arveson had in mind. So a C-star extension is well, a C-star algebra that you generate in some realization. So what you do is you take a complete order isomorphism inject it into a C-star algebra, and then that C-star algebra should be generated by the image. So it should be the smallest in that sense. So that's a C-star extension. But you may realize an operator system in many different ways, because the only thing you have to respect is the complete order structure. And there's no product, so it's actually quite free what you can do in a certain sense. And the C-star envelope is the smallest among those. So that's the A in this diagram, for which any other C-star extension to B actually surjects, and there's a unique surjection. That's the universal property. And so what you already realize is that if you try to find it, and this is exactly what Hamana did, you may want to start with any Caesar extension and then try to quotient out some ideal, this surjection, and then realize the smallest of those. So look for the largest ideal that you can quotient by without losing information about the operator system. And that's actually called a Shilov boundary ideal. You're muted, Piotr. I don't know if you want to say something here, but
So I forgot, yeah, I didn't click properly on. I'm sorry. Yeah, let me just ask a silly question. You say a sister envelope, so does it mean that you can have two different ones?
well,
It's not.
from this diagram you can show they're actually isomorphic because if you have two of these, then there will be the surjections in both directions, and you're done. So the universal
Okay, so it could
property,
be.
as usual, actually gives you the unique one. But in principle, you may want to define this universal property without having that
Okay,
uniqueness.
so until you prove it, you say A. All right. Okay. Now,
Now
is
we're
it
getting into
obvious?
the
Is it obvious that if you take as a unital operator system a unital sister algebra, that the sister envelope will be exactly the starting sister algebra?
No. So let me give an example here.
Okay.
So here, I think this is what you had in mind. So if you take a closed
Mm-hmm.
disk and you look at
Yes.
so in the ambient Caesar algebra being the continuous functions on the closed disk, but you
Mm-hmm.
look at harmonic functions on the closed disk.
Mm-hmm.
So that may be a Caesar extension, these continuous functions on the closed disk.
Yeah.
However, the map, which is restriction to the edge, namely the circle, this turns out to be a complete order isomorphism. And this is because you're solving it's a harmonic function. So you know what you have from the boundary value. And it turns out that this Poisson kernel that you use for this to reconstruct the harmonic function from the boundary value is actually respecting the positivity. So that's actually an order isomorphism. So this is a case where you have sort of the natural place to look for this operator system. So as a function system is actually not the smallest. So the smallest is actually then the C of S1. And in the sense of Hamana, what you find is that it's completely irrelevant for the harmonic function to know what happens in the open disk, because you already know what will happen there from the boundary value. So it's just
Okay. This is not what I had in mind,
go
but
ahead.
let me first ask if this effect you just showed us in this example depends on the topology. What if instead of a disk, I would take the Mobius strip? And when I look at the boundary circle of the Mobius strip, because I know that there are some substantial differences in properties. There's some famous theorem of Smale that something works nicely and functorially for the Mobius strip but not for the disk, but I forgot exactly what it was.
I think this may fail, yeah. So I don't, well, I don't know, but it doesn't look very promising if I think about it for a while. But
Yeah, no, it's just what came to mind. But in fact, this is what I had in mind was something different because you take a sister algebra inside, you find some operator system, then you take the sister algebra of this thing inside, and then well, I'm not surprised that it's not the same sister algebra. But if I just take the sister algebra, a unital sister algebra as my unital operator system, and then try to do the sister envelope, will it be the same sister algebra?
yeah, that will be the same, yeah.
Okay,
So
thanks.
if you ask if the C-star envelope of a C-star algebra is the same, then it's true.
Yes.
But what I'm
Okay.
saying here, so this first of all, this C-star extension that I start with is actually generated by the operator system. And so it's not some kind of artificial smaller such C-star algebra. It's actually that thing is called the C-star extension. So it's being generated by this
Mm-hmm.
image of kappa.
Well, it just shows that well, you can be generated as a sister extension. It's not the same as a sister envelope, right?
That's right. Yeah. So you could realize, and that's really something that you do by realizing it in a different C-star algebra or acting on a different Hilbert space, that you find something which is then smaller in this sense.
Mm-hmm.
Also see Ali? with the
Yes.
question?
Ali, go ahead.
Excuse me. Is it obvious that the order unit in a unital operator system is unique up to positive scalar multiplication?
So it's a definition. So the order unit should be positive.
No. My question is that is the order unit unique up to a scalar multiplication?
No. So I think you can have several different order units. It's a good question, though. Yeah, I would say so. There are several possibilities. Already, if you think about maybe direct sums, you could already sort of play with the scalar multiples that you just mentioned. So you can take the identity somewhere in the in direct sum decomposition, even of Caesar algebra, and then one you multiply with another scalar number than the other. So that's fine. Actually, any positive, in that case, I mean, I would take just a positive something like for matrices that's easily done. Just a positive matrix will also do.
Mhm.
So,
Yes. Okay. Thank you.
thanks. All right. So let's look at the realization of this because it's still somewhat abstract. Also, this quotient. So what was actually the idea of Arveson was to concretely realize this Caesar envelope. And what you want to do is you want to find certain representations which capture some information about the operating system, and then take all of those boundary representations, that's what they're called, all these representations, and that will actually realize in a concrete way the C-star envelope. So what we start with is we take E inside C-star of E, so some C-star algebra generates. And then we look at those boundary representations. So they're the following things. So first of all, they have the properties that if you have a UCP map of E into B of H, then there's a unique extension to C star of E, and that's a star representation. So it has a unique UCP extension, which is then a star representation. And that's the unique extension property. And then if that star representation is irreducible, it is called so-called boundary representation. And the only thing I would like to use from this is the special property, is that all of them will sort of capture for instance, the norms in all of these for all of these elements in the operator system. And so that if you would take their direct sum, you would actually find, so that's what's happening here, the direct sum of all these boundary representations get you into a completely isometric map, which is actually the C-star envelope. So there's a construction of the C-star envelope rather than a quotient, and you may pick the one you want. And this was done about 10 years ago in this paper it's on the top, with a series of papers. So now let's, so knowing that we have this C-star envelope, let's look at some structure, for instance, how to distinguish. And one of the questions is how far is an operator system from a C-star algebra? And what we introduced in the paper with the Lancon is that we have a so-called propagation number, which is the smallest integer, such that if you take, say, polynomials and the closure of those up to degree n, then the smallest of those n's is the propagation number whenever that's a C-star algebra, this closure. Okay, so you just look at, you actually propagate inside the C-star algebra, and at some point you actually hit everything of the C-star algebra. And if you think about the harmonic functions, so that's, of course, I mean, if you think about just the harmonic functions with their products, then that may not be the C-star algebra, of course, because the product inside the continuous functions on the closed disk will not give you harmonic functions. So you lose that property. So you may want to wonder, so when do you actually get that? Now, what happens is that if you restrict to the boundary, that's actually already a C-star algebra. So you're done at once, and you have this propagation number equal to 1. Now we'll come back to a few examples where this also is illustrated. Some properties of this is that, first of all, The reason we designed it was to find invariance under complete order isomorphism. So that's actually not too difficult to check because it's all factorial, or it's the universal properties of the C-star envelopes that you use here. The invariance is actually somewhat stronger. It's also invariant under Morita equivalence or tensoring with the compact operators, which is down here. So that's the second ingredient. And more generally, there's been a notion of propagation numbers for the minimal tensor product, which was done by Ian Coates as a master student. Yeah, Adam, go ahead.
Sorry, very basic question. Is it obvious that it is always finite?
No, it can be infinite as well. Yeah, so that's
Okay.
what we also allow. If it doesn't happen for an integer, then we call it infinite. Yeah.
Okay. Okay, thank you.
And I will also give examples of that in a moment. So, okay, so that's say for preparation. Let's dwell into an example, which is S1, the circle. And so let's look at spectral truncation. So the kind of in the first class of examples. And then what we find is we have, it's like doing Fourier theory with a finite number of Fourier modes. And we project onto the span E1 to En, which are actually the eigenvectors of this Dirac operator on the circle. But it's just a derivative, so that's rather easy. Then if you compress C of S1, you actually get an operator system, and they're formed by putting the take a function f and take the Fourier coefficients, which I denoted with t, and you put them on the diagonals of this matrix. So that's a Toeplitz matrix. And of course, only if a certain number of Fourier modes will make their appearance, because if they're too large, it will actually move out of the range of the projection, so you won't see it. So these are finite dimensional matrices. And what we showed is that if you look at, first of all, what does it generate? So it sits nicely in the matrix algebras, M and C. But what we can show is that you can take products, so degree 2, and linear combinations of Toeplitz matrices to generate any matrix in the n by n matrices. And this is meaning that the propagation number is equal to 2 independent of n, which is an amusing fact, I would say. So that first of all tells me that the C-star envelope is MNC, and that's because we showed it's a C-star extension, but MNC doesn't have any non-trivial ideals, so I cannot quotient out by anything, so I cannot subject into something smaller without losing any information, and that's actually then telling me that this is the C-star envelope. As I said, states are defined, this I already said in general, as unital positive linear functionals. So let's look at the structure of this. So I would like to understand, the main point is to understand what of the geometry, namely the circle, am I describing by these operator systems? Yes, Adam.
Is it right to think that this fact that this propagation number is always equal to 2 somehow relates to the dimension of your space?
It's independent of the dimension, right? Oh, the
dimension of a
one.
circle,
Oh, so we proved it also for the tori, so it's doesn't matter.
It is still equal to 2, yes?
Right, yeah.
Okay, thank you.
Yeah, thanks. That's the work with Malte Lijnberg, actually. He was also around that song. So let's look at the geometries describing or the space of states. So for that we introduced actually a duality. So since this is finite dimensional, it's quite convenient to think about dualities and not so problematic, maybe with respect to the infinite dimensional situation. So that we dubbed Végéry's operator system, and it's dual. First of all, in the sense that rather than truncating in this Hilbert space, we now truncate in the algebra in a sense. So what we do is we take finite support condition, so it's a Fourier truncation, where we say, well, the Fourier coefficients are 0 from a certain point onwards. And then we say, well, positivity is just as a function on S1. So it's all sitting in C star of Z or C of S1. So that's where you get the notion of positivity. The C-star envelope is then actually realized to be all of C of S1, because so first of all, you find that the support grows under the convolution product, for instance, in Fourier. So you find that the propagation number actually is in this case equal to infinity because the support was finite and you need infinitely many products to get all of C of S1. So then, so first of all, let's look at this operator system and forget for the moment about this this duality or about these Toeplitz matrices. So now this one has the nice property that if you think about the positive elements, you can describe the extreme rays in there as those elements A, so these are these sequences up there, for which if you look at the Laurent series, then all the zeros lie on S1. And this is actually a nice proof where you say, well, if it's a little bit off S1, then you find that there will be one outside and one inside the circle, and then combine it into proving something is not positive. So it's actually quite nice. The pure states is something interesting as well. So if you take C star of Z truncated at level n, then you know that the pure state will extend to, in this case, the C star envelope, C of S1, also as a pure state. And there you know what they are. They're the evaluations at the points of the circle. So you just have to make sure that you get all of them. And here the mechanism is that, well, you get maybe one of them and all the others are obtained by using the invariance with respect to the S1 action, the U1 action. So that's so these truncations are they have a lot more symmetry, as for instance if you would take cyclic groups as an approximation of the circle, because I do at all times have this S1 or the U1 symmetry behind the scene that is helping me a lot in getting a lot of nice geometrical structure out. All right, so we called it Fégéries, and that's because their lemma of about more than 100 years ago is used in this duality. And so it's used to prove that these operator systems are in duality in the sense that cones of the positive elements are characterized by the functionals acting via this duality. And in there you used Fégéries' lemma. And actually that extends to a duality of operator systems where we proved it only for level 1 to all levels. And that was done by Doug Ferencik. Then using a Fégéries lemma for operator valued functionals.
Sorry, something is missing in this formula. T with subindex, it's only minus k?
Yeah, k runs from minus n to n.
Okay.
So T are the
Okay, there is one index in this T. Okay.
That's right.
Okay.
Yeah. Yeah, because they have constant diagonals. So it's not just a matrix. The matrix actually only depends on this T k minus L in this case.
Okay, it makes sense. Sorry for that.
Not a problem. So what you get is, but you can actually now revert this previous proposition because I have a duality. So if you have a duality of operator systems, then the extreme rays in one cone of positive elements will actually be the states on the other operator system, just by definition. That means that the extreme rays in the Toeplitz matrices, in the cone of positive elements in the Toeplitz matrices, they're actually they're given by these rank 1 projections that you have for any lambda in the circle, while the pure states, they correspond to these zeros that I had to choose in these elements which are the extreme rays in the dual. And this means I have n points on the circle up to permutation. So that's this quotient up there. So that gives me the information that I would like. So somehow this is supposed to reflect the structure of the circle. These endpoints, they are sort of reflecting what I started with, namely the circle. But let's, before I'm doing that, let's look at the first point, the extreme rays. So this is, and again, an odd result, but now of Kara-Theodori, which tells that if you take a positive Toeplitz matrix, you can actually decompose it. You can sort of diagonalize it in a certain sense. And the way you do that is the following, and that's this theorem, but now it's a corollary of the duality. So if you take an n by n Toeplitz matrix, then you get a positive. It's actually positive if and only if it's of that sort of diagonal form, where V is this type of van der Monde matrix, where the lambdas are the points on the circle. All right, so that's that's what we have in this context. So let's look at let's see. So I have a few remarks on the sort of this is sort of at a fixed n, and an amusing fact, but I will only do that very briefly, is that if you look at the sort of what does it actually describe, you want to compare these state spaces, and this is actually in the sense of Mark Riefel of these quantum metric spaces that you have at each level to the limiting case. So the way we do this is the following. So we actually compare, this is a general result. So you have a sequence of operator system spectral triple. So that means I have some kind of notion of a spectral triple based on an operator system. Then I have these maps going back and forth between the limiting spectral triple and the EN, and then and also the other way around. And what I want, so the main point of these formulas is that I have that they're each other inverse up to some control parameter. Okay, and that's actually with respect to the leap norm. So I have this sort of sequence of gamma n and gamma n prime that makes sure that the Rn maps and the Sn maps, they're actually each other's inverse. And in that case, so if you have such an approximate order isomorphism, then the state spaces converges. So the state space of this whole sequence actually converge to the state space of the limiting spectral triple with the metric that you get from there, as I showed in the beginning, in the sense of Gromov-Hausdorff convergence. So you're comparing metric spaces, and there the Gromov-Hausdorff distance goes to 0, depending actually on these gammas that I have over there.
Oh, sorry,
So
it could be applied to this previous example?
Yeah, it can. So I will show it now.
Okay.
So in this case, and if this is what you're asking, so in the case of the circle, I apply it indeed, and then what you get is, first of all, this one map is the compression map by the spectral projection, Pn. And so that means that somehow you can have you can pull back states that you have on this triplet system to the circle. And this pulling back is actually the map that gives rise to this comparison in Gromov-Hausdorff sense. There's the other direction, which is actually trying to get from such a triplet matrix to a function on the circle. And so there you have to be a little bit more careful, because you cannot just take these Fourier coefficients that you have in the triplet matrix and write the corresponding function, because that will not be, in general, an order a completely positive map. So what you need to do is you it's more like so underlying here is what you see in the formula is a convolution with the Fagier kernel. And then what you find is that the sequence of state spaces actually converges to the state space on the circle. So the probability measures on the circle in Gromov-Hausdorff distance.
Sorry, but I had in mind this second example with this Fayer with finite support, since, correct me if I'm wrong, the state space was n torus divided by permutation, yes? Symmetric.
No, that's this one. So the state space of the triplets operator system,
Yes.
that's the one you just said, the n tori divided by the permutation. And that's actually approximating the state space in of the probability measures on the circle. And it does it by putting weights on these points, in a sense. So it's like a measure which has centered around these points that you distributed over the circle, in the sense you just described. And so that was actually done by Eva Maria Heckelman. So in these 2 papers, so one I showed that all the state spaces, which is all the states, if you look at all the states in these state spaces, they converge to the probability measures. What Eva Maria Heckelman showed is that this actually applies to the pure states as well. So they will already Gromov-Hausdorff converge to all probability measures on the circle.
So how it could happen, since your spaces are of larger dimension, yes? The dimension increases to infinity, and somehow finally it converges to something one-dimensional? Regarding this pure states, it not applies to all states.
No, it does not converge to the pure states on C of S1. It's converging. So I take pure states at all the finite dimensional levels.
Yes.
They will actually converge to the state space of C of S1 being probability measures on the circle. So that's already sufficient to take those.
Okay, so your sequence is restricted only to pure state, but the limit is always the whole
That's
space
right.
of states.
So you can restrict it. I mean, it also applies to the whole state space, but in particular, so what Heckelman showed is that it actually is, or you can do this for the pure states of the tuplet systems, and they will converge to all probability measures.
All
And so
probability. Okay.
it's like smearing, right? So and it's clear that so in all these maps you don't respect any of the convex structures so much. So it's really it's at least there's no contradiction.
Okay. Okay. Thank you.
Okay, so that's for the truncation. So many other examples. In fact, I've been working quite intensely with Malte Leimbach, who will event on Monday. Actually, we're looking at spectral truncations of tori, Peter-Wout truncations as well, even for quantum groups, compact quantum groups. And so there are some names here that also have this similar kind of approach, where you have these maps going back and forth in an approximate kind of inverse way. And the Fourier truncations that I described, so the ones in which you have support conditions, they actually also converge also to the circle or to CFS1. And that was actually generalized by Mark Riefel a few years ago. And then again, in a more general context of compact quantum groups. So that's a very lively area of research. That's quite nice. I mean, I'm still, the open question is still, if you take a spectral triple and you do this sort of general, you have the sequence of spectral projections for D, the question remains if that still converges to the thing you started with, or the state space at least that you started with. So that remains an open question. All right, let's move on and take this. So we have a small sort of interlude of these sort of integral kernels. So we dub them to be bonds. And so in general, they arise as follows. So you take we take a locally compact groupoid with a Haar system, and so this is rather general, but the point is that inside that groupoid, you take a subset surrounding the diagonal or surrounding the units, which is also symmetric. And instead of looking at the full C-star algebra associated to this groupoid, so this one, you look at the closure of the subspace with support on that omega. So you just restrict the support and do the same kind of thing that you do for the universal C-star algebra construction. So that's what we call that's actually an operator system. And so if you would do this for Lie group, locally compact Lie group, or even let's look at the Lie group G. Then you take omega, so that's only containing the unit and being symmetric otherwise, and so on the inverse. Then you get Fourier truncations in C star of G in the sense of Riefel. The one I already showed you is Fegeri, so then you take a particular minus n to n, so these are special cases of the first example in Z, and that's the Fegeri's system. And interestingly, if you would do the same, but then in a cyclic group, you take the same omega n, but the C-star algebra is different, then you get a completely different order structure because you get it from C-star Cm, and that actually is completely different. And the operator system is then that of banded circulant matrices where you have a fixed bandwidth n. So that's indeed different from the Fegeri's system. And the propagation number is now finite and so on. So one case to which is actually the model for what is to come, the infinite dimensional version, is if you take a finite set, you take a relation which is symmetric and reflexive, then you can do the same thing, but now since it's a finite set, the groupoid C-star algebra will just be matrices. So what you get is the C-star envelope of this, what you call E of R, is actually the compacts, but that's just M of XC, so just the number of elements. The propagation number is then related actually to the to considering this as a graph. So that's the diameter of that graph, where you say that R is a graph, of course, in the usual sense. Now you may wonder, so what is now the order structure of that of the dual, for instance? And so the duality is just by kind of pairwise putting these things together, sort of Hilbert-Schmidt way. But since in one you say, well, the matrix should be positive, in the dual you find that you have something like, well, the part of the matrix that you see in the duality should be positive. And then in the case of a chordal graph, you can actually realize this concretely by saying it's a partially defined matrix, which is then partially positive. So that's a very nice and elegant way. And here's something about the pure states, but let me actually bring this to the general case of a metric space, because the kind of the motivating example that we had in mind, and where we use this finite description, is a metric space where you have a relation, the one I gave at the beginning as a motivation. So you take this relation inside x cross x, where you take 2 points to be related if their distance is smaller than epsilon. Then you can look at indeed this operator system. I call it E of R epsilon. And this is, of course, realized as the closure of the integral operators with support in this R epsilon. And this all sits inside the compact operators, which is the groupoid Caesar algebra for the pair groupoid, x cross x. Then you find that, first of all, you need some assumptions on the compatibility between the metric and the measure. But it's other than that, that's quite straightforward to check that if you take the Caesar envelope, or let's look at the Caesar algebra E of R epsilon generates, then that will be the compacts. And the compacts have the same property about these ideals, that you cannot quotient out something because the ideals will be trivial. So you end up with this being the Caesar envelope. And you actually find that it propagates by growing support, so that at some point you hit the diameter of the space X, supposing it's finite, otherwise this number is infinite, and that's what you have as a propagation number. A nice property also about pure states is somehow thinking about what does the compacts do. So they have pure states, of course, being vector states, like this. And what you have as an additional assumption for this to be still pure if you restrict, is that essential support of this psi should be sort of epsilon connected. So it cannot be too far away if you look at the support of psi and the connected components of these with respect to the metric that I have on X. So that's sort of geometrical explanation or understanding of what the pure states or the points are that you're describing with this operator system. Okay, let's go on. And that's sort of this is the other sort of approach. But let's come to maybe the second part of the talk, which is also the title. It's about K-theory. And so what I would like to describe is, first of all, I will give a wish list of what K-theory of operator systems should be, and which is actually motivated by these facts that I started with, that you have these rather effective definitions and of operator systems and results in that field, but also these examples that really work very well, have a lot of structure, and they really capture also the limiting case. So the question is then, so can you also capture some of the more sort of homological data, so K-theoretical information from the limiting object that you're trying to describe, but at the level of these truncations? And more generally, so what I'm striving for is an invariant, which is like K-theory for Caesar algebras. And so the first thing is then, of course, okay, well, how does K-theory for Caesar algebras work? And so in K0, which is what I will focus on today, so you need something like projections, but projections immediately ask for a product. I mean, star will be fine, but the product is not. So we have to do something better than that. So there's a notion of projection in an operator system, though. So this is due to Araiza and Russell, and it actually is, so it's characterized in terms of the operator system, and it's a projection if and only if it's a projection in the Caesar algebraic sense in the Caesar envelope. So that's nice. However, from the spectral truncations, we actually know that if you would take a projection in the Caesar algebra and you compress it, it will typically not be a projection. So that's something to keep in mind. And in fact, invertible self-adjoint elements may be better suited for that. And so motivated by this Loring, Schulz-Baldus, and other people, spectral localizer, you find that somehow the spectral localizer capture the index information, and and it should be in the same terms that you capture this at the operating system level. Moritek invariant should of course be also on the wish list, so that should be around. And tensoring the compacts is the most convenient way to deal with this, of course, as usual. So that's what we want. Now,
And how about homotopy invariance?
No, that's actually that's more complicated. I will say something. I mean, homotopy will be around, but not in the sense of the C-star algebras that you have in mind. So, but
Okay.
it's a good question. So it's open for research, I would say.
Okay.
So if you reconsider, so take a slightly different perspective on K-theory, there's a very nice way to do this is by looking at Hermitian forms. Actually, it's in the sense of width, and that's the perspective I'd like to take. So it's the width ring or the width invariant, and so let's look at this for unital operator systems. So what you do is you take a self-adjoint element in M and E, which is in a certain sense non-degenerate, and the non-degeneracy is measured by looking at all these realizations, which are actually the boundary representations that I already explained. But you look at all the pure and so-called maximal UCP maps, so they cannot be extended beyond that in a non-trivial way, which are bounded from below in absolute value. So they have a sort of a gap if you think about their spectrum in that realization. So in all of these realizations, it has a gap in the sense of physics, or in the sense of the spectrum lying away from zero. And the G is sort of fixed. So there exists a G for all of these boundary representations. And this means that if you look at the C-star envelope, then you find that this is actually non-degenerate if and only if its image in the C-star envelope is invertible. So that's somehow capturing this property of non-degeneracy on the operating system in terms of something that you can easily check, namely in terms of the C-star envelope. I write HEN for that, and the fact that this proposition holds is actually because of the realization I explained of the C-star envelope. Okay, so let's look back at what we may have then. So first of all, in the sense of width, so we have Hermitian forms on finitely generated projective, right modules. Then, if you think about a Hermitian form, then actually it's of the type it's given by the matrix of the form, so that's called H, and that matrix H is inside P, M, and A, P. So that's actually the corner now in the C-star algebra M and of A, because P is a projection in with values in A. And what you do is you add to that H, you add a sort of trivial corner, which is 1 minus P, and these Hermitian forms are then can be used. There's a map which brings you back to K-theory of the C-star algebra. So that's why they may be of use in this context as well. After all, we have this notion of matrices over the operator system. So that's really crucial information that we like to keep as well, but we have it similar to the case of C-star algebras. Projections in operator systems, they are actually projections in the C-star envelope. So indeed the spectrum of this element X, which is E minus 2P, that's a Hermitian form. So Hermitian forms being indeed the kind of decomposition into the positive and the negative eigenvalues of my of this Hermitian form. And then what I have in mind is that you project. So the projection is the one corresponding to the negative eigenvalues of the Hermitian form. Third is if you take epsilon projections in the sense of Oyonnax in U, so that's in quantitative or controlled K-theory. So these are projections that were introduced in the context of filtered C-star algebras, where they're not really projections, but they're almost projections. So they're like P squared minus P in norm is smaller than an epsilon. And their epsilon is typically smaller than 1/4 in their papers. And that actually guarantees that this E minus 2p is still has spectrum away from 0. So it's still invertible in the C-star envelope. So that's an Hermitian form as well. So you also capture this. And if you think about filtered C-star algebra, so the filtration actually gives it's sort of a nested operator systems where there is some relation to the product of the C-star algebra, but after all, each component is an operator system. And the other thing I would like to capture, which is an example, if you take a capital Y, which is coming from a C-star algebra, which is the identity minus 2p, then you can also compress that with the spectral compressions or the truncations that I described. And you have to make sure, so that's something to be tested, that the X still has a spectrum away from 0, and that's somehow the ingredient that you need. And that may fail at some point, which also tells us that in general, if you take like a realization of UCP maps, then this will actually, it looks like a special case, but it's actually a general case, because UCP maps can actually be factorized in the sense of this by using compressions, by projections, by a Stein-Spring representation. So there you actually find that UCP maps may not respect non-degeneracy necessarily. And that's not something that I think is, that's something to be sort of appreciated. So I will come back to that later on as well. So let's look at some properties. So first of all, we look at this modulo homotopy, and that we do at each level. So I'm introducing these non-degenerate elements on the right, and I look at homotopies of elements in there. So inside these matrices of size n, and that I call V. That's my candidate for an invariant. And since my maps are complete order isomorphisms between, say, E and F, it's clear that all structure will be respected, and you find that this is indeed an invariant in that sense. Let's look at an example, because for C-star algebras and even C, just the complex numbers, what you find is that at each level, I'm looking at n by n matrices up to homotopy. So n by n matrices which are self-adjoint and invertible. So then you think, and then it's not so hard to figure out that you need just a signature, or say maybe what I wrote here is the signature from running from minus n to n, and that's actually my set up to homotopy. So these Hermitian elements up to homotopy is equal to that, and you can connect all of these invariants by embedding it and extending it with the units. So that's as compared to projections. I add not 0, but I add E, and that's considered to be sort of the neutral element eventually. And so these embeddings, or these maps, I should say, these embeddings in these between these sets, they're actually compatible with taking the number of negative eigenvalues of my invertible matrix, which is called this rho n, which is the negative index of inertia. And that's all compatible, which is suggesting that indeed the invariant that you get is the natural numbers when you take a limit. And indeed, I mean, in general, what we do is we have such maps I, and along these maps, so we map all these VEN into the next ones, and then take the direct limit along these, which just means that if you have two elements in there, then they're equivalent if at some, say, next level, one of the next levels, they're homotopy equivalent. And then you may take the Grothendieck group which has the identity as a neutral element. So you add E's rather than zeros with projections, because I'm looking at Hermitian forms. And the addition is, of course, the direct sum. But it's actually more interesting to think about what is the invariant at level n. So that's what I actually keep, because they may be more refined. And a nice example here is that if you, so it's about unitaries, but the same story holds for K1. So if you would take a unitary U and V, then what you can do in K-theory is that you may take their product, So that U times V may still work out as a new element. And then what you show is that actually UV extended by the identity, so direct sum with the identity, is equivalent by white hat to U and V on the diagonal. So rather than taking a product, which is what we don't have, we can do the direct sum where we have to allow ourselves to enlarge the size of the matrix. But that's something we do have for operator systems. So that's why there's a lot of room for this to work. And that's what you find back in the K1 case and more generally. So let's look at some properties. So first of all, if you take C through algebras, then actually there's a usual map, which I should probably say it's a very nice paper that I also refer to in the paper I wrote on this of Rosenberg, where you have this realization from these Hermitian forms to the K theory by taking essentially this signature. So projecting onto the negative eigenvalues of the Hermitian form, which is what this map does. So you take this realization. So that's what you get, and that's giving me also the fact that indeed you're describing K theory or K0 for C-through algebras. The other nice property that we should have is stability. So for that, what we do is we take the following map, which is a map from the n by n matrices over E to the n by n and then times 2, so that with entries in the 2 by 2 matrix over E. And what we do is somewhat awkward maybe if you look at it at first sight. You take these blocks and you sort of apply these embedding maps that's suggestive of the compact operators, but on the diagonal you add E, and off the diagonal you don't. And I will explain how this actually may realize this stability. But for that I need a bit more time on the non-unital situation because we're dealing with compacts. But what you can see already at this point is these elements this matrix here, this is actually homotopy equivalent to X because first of all, you have to add this E to it, and that's the trivial element, that's the unit. And then you have to rearrange these columns and rows, and that you can do, but you need to extend to larger matrices. So like with white hat in the case of C-through algebras, it goes exactly the same. You just reshuffle these things and you find that you have your X in the corner and E in the bottom corner. And that's sort of showing you at least that K0 of E is the same as K0 of 2 by 2 matrices over E. So that's sort of the starting point for stability. And this works in general, of course, for Mn of E, capital N. So let's look at how this can actually realize stability, where you usually take the compacts to be realized by adding zeros and not by adding units. So that's something to figure out. So what happens is that, well, the compacts are non-unital. So first of all, we need a definition of K theory for non-unital operator systems. And so Werner has a notion of non-unital operator systems, which is based on the use of states, actually states on the operator system, where you use that, first of all, to have some notion of a norm, and then that should be compatible with the operator space norm that you're given. So there's some kind of compatibility. But what I want to highlight here is the following, is that you have a unitization in that context. So we work with this. We have E, we add to it the complex numbers, that's E plus. But the matrix order structure is actually coming from this from these non-commutative states that you act with on this operator system E. So these S and E are duals of n by n matrices over E, and they're still states. And so that's the notion of positivity that you have in this E plus. Now, if you want to define an invariant at level n for a non-unital operator system, what you say is, well, actually this matrix in the C component, that should be homotopy equivalent to the identity. And then you take a quotient again by homotopies. So that's sort of what you allow yourself to have for non-unital, which is the V tilde that I have. And in the case that E is unital, then actually you can maneuver this E plus into E plus C, but now with the direct sum order structure. So just the fact that you have cones in both of these. And the way it goes, it's like with C-star algebras. For the unitization, you get that XA is actually mapped to X plus AE, comma A, so that you don't lose any information in taking the unitization, say, or add information that you don't want in the unital C-star algebra case. But that actually shows that in that case, the invariant of E, of the unital operator system, is the same as the invariant I already had. So the invariant V, E, comma N. So that's sort of the setup. And then the theorem states that if you take the same procedure, you look at the non-unital operator system, which is E times minimally tensor product with the compacts, then I claim that the K theory is the same. And actually, it's the direct limit semigroup, which is the same. So this V tilde is actually the same instead of writing that for K0. So here it is again. So let's sketch the proof of that. So the first thing is that we, of course, the stabilization of these of the underlying C-star algebras, or the operator systems, excuse me, are the n by n matrices, and you map it into larger matrices by extending it by 0. That's what you use to realize the stabilization tensoring with the compacts. Now, how does this transfer to the formula I showed with the iota, which is this extending on the diagonal, not with 0, but with an E? Now, that's how it goes. Because under the realization that I just showed you of this V tilde to V for an unital operator system, you find that this kappa map, which is just extending it by 0, becomes the map iota n that I had before. So, and this is actually the map that that does put E's on the diagonal, precisely because that's the formula that I was giving you before in this identification of the E plus with E plus C. So that's underlying this this fact. And then what you have to show is really, so first of all, I have this stability at the level of, say, E to M capital N of E, and that sort of goes through. And as usual, you have to argue that if I have a homotopy in the compacts, then I actually can compress it to a homotopy in the finite level. So that's proving inductivity at these levels, at these finite levels that I am now completely controlling by this diagram. And then surjectivity is a similar thing as with C-star algebras, that you approximate by finite rank operators in norm, and then you don't lose the property of being an emission form. That's again the subjectivity of this. And that shows me that this invariance V or V tilde of the compacts times E is actually isomorphic to the semigroup V of E. And so in particular, it applies to the Grothendieck group. Okay, so that's as far as the sort of the general construction is concerned, or what I wanted to show you today. Let's look at some applications of this, because actually it's quite applicable. So first of all, a nice thing is that if you reconsider these Toeplitz matrices, you may wonder, so what kind of invariance do you have at each level? And let's just start with the basic example. Take Hermitian forms in the Toeplitz matrices. And let's do this at size 2. So a 2 by 2 Toeplitz matrix, which is like this. And then you have to show that, well, this should be invertible, so the determinant should be non-zero. And that's just giving me the following picture, that you have this plot of the parameter A and the parameter Z, or absolute value of Z. And in that picture, you find Toeplitz matrices, and there are 3 areas, which are then, say, the homotopy equivalent within a, and they're separated by this line where, of course, the determinant is equal to 0. So you find your element minus E, and E is the trivial element, and there's sigma 1. And sigma 1 is the Pauli matrix, which is 1 of the diagonal, which is indeed a Toeplitz matrix. However, if you try to diagonalize it to, say, 1 minus 1 on the diagonal, that's not a Toeplitz matrix. So it's slightly different from the sort of ambient C-star algebra, but still you get the same number of invariants. So there's a lot of information around. And the same actually, it propagates to so higher levels, where you say, well, if you take 2 copies of sigma 1, so these are these 2 Pauli matrices that you add, then actually you cannot diagonalize them, but what you can actually do is you can so diagonalize them as a block matrix, in a sense that you put E and minus E, and that you can actually realize within the space of tuplet matrices. So you have to sort of find your homotopes not in the C-star envelope, because otherwise we just do some intersection of the K-theory and the C-star envelope to being represented by those elements in the operator system. No, we actually do something which is specifically for the operator system, and the homotopy should be in there. That also makes it more complicated, of course. So to compute these groups, that's quite a challenge and still open. But fortunately, there's a device to check the non-triviality of certain elements, and that's the spectral localizer. So in the next few slides, I will show you this in action, because that's a very concrete and well-known example, is that if you take the 2 torus, then you may generate K-theory by looking at projections like this, 2 by 2 matrices, and they're very much like Power's refile in the case of the non-commutative torus. So it's somehow interesting that came before, and then Terry Loring in his thesis showed that you can also do this on the torus, but of course you need to go to 2 by 2 matrices, because you will not be able to find projections in the torus itself, because it's a function algebra. So what you do is you take functions f, g, and h. They are depicted here. So they're f and g and h.
Sorry, may I briefly interrupt you, because this is very interesting for me. In what sense they are analogs of this Power's refill projection? Can you say it again? How do you see Power's refill projection in this 2 by 2 matrix?
So Power's refill also have the f, g, and h functions.
This I know, yes.
And they satisfy the same properties, except that there you don't need to work with the 2 by 2 matrices. You write it actually on the algebra, but otherwise they satisfy the same property. So that's what I mean.
Okay.
And that's of course because
so basically use the same functions f and g, right? That's
yeah.
okay.
So G and,
okay.
I think I have G somewhere here in green and H in yellow, and then F will be the one in blue. So and they satisfy the properties that I would also use for Power's refill.
Okay, so I know it's not relevant to your talk, but let me mention there's some magic about this. I call it Loring projection, because it's the easiest formula. If you apply the bot connecting homomorphism, in K theory, when you have a 6-term exact Meyer-Vittori 6-term exact sequence in K theory, and you are out of a projection in 2 torus, you say you produce the generator of a K1, you say in some quantum 3 sphere. It's funny because the unitary that you get is exactly 1 by 1. If you look, say, at the graph sister algebra as your 3 sphere, you get exactly the unitary that you should get as dictated by graph sister algebra. So this projection of Loring is quite a magic.
I see. Okay, that's great. Yeah. No, it's beautiful. So it's so here what happens is that you can work with this projection. So choosing these functions g and h and f in the first, I think the first variable, yeah, but it doesn't really matter, and using the other variable. Then so what you can analyze is what happens to this projection, which is indeed a generator of K theory for the torus, is that that you truncate it. So you look at spectral truncations, where you say, well, I will look at some kind of region in Z2 corresponding to the eigenvalues of the Dirac operator up to some scale rho. And so that's depicted here. So that's the closed Hilbert subspace. And you compress onto that. And what you do is, so there's 2 P's, one should be a little bit careful. Capital P is the compression. So that's really the spectral truncation. And then the Loring, or the Power's refill Loring construction, is small p. And the emission form is capital Y. So that's 1 minus 2p. So that's the thing which is indeed invertible. So that's the invertible element, and I'm compressing it, hoping it, of course, still to be invertible. And this one can check in some cases that for p, for certain p or certain rho, this will indeed be Hermitian forms. And so then you end up in the K-theory of my operator system coming from this spectral truncation. And the question is then, so how much index information do these carry? So, and this is something that for which I use the spectral localizer, which is a construction of Loring and Schultz-Baldus and then other people as well, is the following thing. So what you do is you look at a matrix, which is a matrix that you sort of build from the Dirac operator plus the grading times the Hermitian form. So that's more or less what you keep in mind. So this is the Dirac operator, which is indeed, it's an even dimensional situation. So I have a D plus and a D minus. The grading is minus 1, 1. And I multiply that with the PYP. And so the question is, do you get some index back from this? And what they show is that there are certain ranges of kappa and rho for which the index pairing of PDP, so small p here, so the one that you have in infinite dimensions, so the pairing between the K-homology class of the Dirac operator represented by the Dirac operator with the K-theory class of the Loring projection, that can be computed to be the signature of this finite dimensional matrix. So just computing the number of positive and negative eigenvalues, take their difference and divide by 2. This is exactly giving me the index. It's a way to compute the index of this of the left-hand side. And this is, of course, a big theorem. So this is rather involved, and it's based on spectral flow. There's a beautiful book, which now contains that as a sort of a treatment from spectral flow, also in the even dimensional case. So that's a very nice situation. Now, what I'm saying here is that my ingredient PYP, which is in my K-theory of the operator system, is only thing I need to compute this index pairing. You see, because that's what appearing in this spectral localizer. It's just an input now. And I have the possibility to do the computation at the level of the operator system, to do the index computation there, even though I'm trying to compute something which is happening at the infinite dimensional case. And this is exactly what Loring and Schultz-Baldus did, which I apply here. So some plots to also to lighten up, because it's a bit late, at least here, in terms of dinner time and so on. So this is the plot of the eigenvalues of this compressed operators Y. So you see that at least 0 is not in the spectrum, so that's good. And maybe more interestingly, is this spectral localizer. So this is what you get when you take this matrix, this localizer, this 2x2 block matrix with these operators in there. So finite dimensional. You look at the eigenvalues. You first of all find that there's a gap, so that's good. And here as well. And these red dots mean there's 2 more positive than negative. And that's really telling me that the signature is equal to 2, so divided by 2, giving me the index equal to 1. So for the winding number of this unitary. Similarly, if you take the winding number to be, say, twice, so the size of 2, then you find that indeed you have 4 more eigenvalues at the positive sides as respect to the negative one. So again, you get this effective way of computing this index from the spectral localizer. And these are easy things to compute and are indeed very effective, also in the context of the work of Schultz-Baldus and others. Okay, so let's come to some conclusions, maybe some discussion as well. So I started with the metric aspect of non-commutative geometry, looking at some kind of partial information that one may have available. So spectral truncations, tolerance relations coming from this kind of finite resolution in the spatial part. Used a lot of duality to consider state spaces, in particular for the circle. The notion of invariance. So first of all, we had the propagation number. That's a sort of a rough. It's indeed just a number. So it's an invariant that you may use. And K-theory. And that can also be extended to higher K groups, which is actually in the transactions of the AMS. So that's where what you do is you don't take Hermitian forms, because Hermitian suggests self-adjoint, and indeed that's the case. But it's rather taking this. It's actually something that that is reflected in this Shamsuddin, Kohn, and Mukhanov have in their quanta of geometry. They consider operators which they actually call y typically, and it's either 1 minus 2p, so projection p, so y squares to the identity, or it's a unitary and the unitary conjugate of diagonal. So as I depicted in this formula, because that has the same property that y squares to 1. So that's sort of the basic building block they use for their description of quanta of geometry. And here it enters, it's sort of as a general formula, both in the odd and the even dimensional case, because I can now say that, well, in either in the even or the odd dimensional case of K-theory, I can look at those elements, I make it Hermitian in this sense, and I have that as a spectral, that has a gap. And I have now a parameter delta, and that's because in practice you may want to control this gap and make it quantitative in a sense. So you take this gap more serious and you take out the homotopy again in the same at the level n. And what you can do is do some Clifford technology to look at Hermitian forms in tensor products with the Clifford algebra to kind of go into higher K-theory, and then formal periodicity is not so difficult to check because these Clifford algebras have that periodicity condition. So that's all it's not getting anywhere close to Bott periodicity, but at least you have this sort of formal periodicity to make sure that these definitions they sort of match and they are periodic of period 2. And they indeed, I mean, they sort of recover K-theory invariance. So some more, so this is in this other paper, more outlook is actually what I want to stress as a final point, is that, so you may think that if you take a UCP map between operator systems, and we saw already a few of them, it may not be true that if you take a non-degenerate element, a Hermitian form, that it will map under this UCP map again to a non-degenerate form. The spectrum actually may hit 0. So there's no real control of that. And so what you actually have is the following perspective, is that these are the compressions, if you wish. So these are like, you kind of get your maps into, say, some smaller and smaller kind of compression, smaller images of the Hilbert space, close to Hilbert subspaces. And then you may wonder, so when do I find classes back from an element which was invertible in the first place? So can I capture these K-theory elements at that level? And can you then check, for instance, using the spectral localizer, that they are indeed non-trivial if they're still there? So that's something that that's sort of reminiscent of persistence of, for instance, persistent homology, where you have some way to detect classes in homology at certain levels, at certain scales of the system. And that's what I'm trying to sort of convey at least and develop. The other direction is more like this filtration situation where you build up the C2 algebra from the inside, and then you have your EK minus 1, EK, so they maybe sit inside the C2 algebra, or at least they sort of map to it. Then you may also wonder, so if you have a class, does it sort of persist and eventually get into a class in K0 of A? And maybe you can use the whole sequence and get invariants at all of these, and they live for a certain time, and then you know that that's an invariant of the whole system, so maybe also of E, a more refined invariant. And underlying that is the approximation of C2 algebras that is being done by, for instance, in the 90s by Blackadder and Kirchberg and F systems, and more recently for all nuclear C2 algebras by Courtney and Winter, where you have a system of actually matrix algebras, but the maps are not homomorphisms, but they are actually so-called CPC maps with a certain property. And then the only thing you know is that, well, they have a certain sort of, they respect some structure, but not so much. It's not clear that the K-theory class will actually survive such a map. So it may actually become degenerate at a certain point. But this I would actually like to see as a positive aspect, where you have this sort of refined structure that you use to describe the K-theory invariants. All right, and that's my final my final slide. So I will stop here. Thank you very much for your attention.
Thank you so much, Walter. Now let me immediately clarify some things. Can you go back to the previous slide, please? Yeah, so do you have some concept of a suspension of an operator system?
No, not yet. So I think these things need to be developed. So yeah, that's a good point, of course. Yeah, it's clear.
So what do you mean by this formal periodicity?
So that's in the sense of Clifford algebra. So it's like a little bit like in KK theory, you also have this formal periodicity where you tensor with CL1 essentially to get the from even to odd. And if you keep doing that, then you use Morita equivalence. Actually, that's also being used here to move back 2 steps. That's it.
Okay, thank you. Now, Jonathan, go ahead. Just unmute yourself.
Yes, really wonderful talk. Thank you so much. I really appreciated this. One question, something you didn't touch on. If you have an operator system and you embed it into its C-star envelope, do you know anything at all about the induced map on K-theory?
Yeah, I think you have that's a good question, yeah. So you should have some would be nice to have some control over these homotopies, of course. That's exactly what one has to look for. So there's for such maps, it's so yeah, let's see what you know. Yeah, I think it's in that sense it's finer. So that's the only thing I could say. So it's so we have being sort of blocked by these homotopies being in the operator system. It tells you more information and think, for instance, about this Toeplitz operator system. I mean, there it's sort of you don't want to move to the matrices, you want to stay within these operator system. But I think that's more or less in general. One can only say that one has to consider the more homotopies that you have in the C algebra. Yeah, but
Right.
that's
Okay.
a very good question. Yeah, thanks.
Thanks.
Adam.
Do you believe that there are some prospects to defining the dual theory, and in particular, a fundamental class of an operator system, like in K-homology?
Yeah, so in K-homology is interesting because if you think a little bit about it, which I did, of course, is that if you take the kind of usual notion of say a Fredholm module or even a spectral triple, then you would say assume it has bounded commutators with the elements in the operator system. But that means it's actually a Fredholm module for the C-star extension that it generates, because it's just a Leibniz rule for these products. So if you have bounded commutators with the elements in the operator system, you will also have them for the C-star extension. So what you actually are after is some kind of notion where you say, well, I want to then say when two of these say different realizations for or Fredholm modules, say in different C-star algebras, when they are equivalent. So you want to have some kind of, you want to impose some notion of equivalence between them. But that's something, again, open. So it's all fresh and waiting to be developed. So thanks for the question. Yeah.
And one more question regarding these spectral truncations. So, how do you view it in comparison to the notion of, which is not precisely developed, but at the level of some vague idea, is there the notion of quantum correction to geometry? That's very often mentioned by Alan Kohn.
Yeah, so I may have said this before, but that was the starting point of this whole project. But we got drifted away a little bit. So the idea was the following, is that if you would want to incorporate quantum corrections, then we found out quickly that for instance, the Dirac operator may pick up some corrections by some kind of higher order derivatives, like logarithms of the Dirac squared or something like this, as you would get from quantum field theory. And then you're actually wondering, so well, that's not fitting in the context of a spectral triple, but you also know that it will only become relevant at a certain scale. So you want to sort of change this notion at several scales. And then we first thought to analyze, so what does it actually mean to look at the space at different scales, at different spectral scales or energy scales. So that's where we got completely maybe overwhelmed by this nice structure of operator systems. But behind the scene, there's still this idea that these operators that define the metric will change along the way when you zoom in. And then you may wonder, how do we actually correct that geometry at that scale? And the
Yeah,
point
but
of... Sure.
okay, continue. Yes, yes.
No, so in a sense that
Mhm.
you expect that so a truncation to happen at a certain scale, so that's finite dimensional, that there's more possibilities to incorporate these logarithms as well. So
Mhm.
you may try to analyze them there. So that's
I just wanted to ensure myself whether I think about it correctly. So you view this this whole Dirac operators as being more classical than this spectral truncation, or the other way around? It's like a more classical limit of something which is more quantum. So the spectral truncations are more quantum, and if we somehow tends if this projection tends to identity, somehow we restore something which is more classical. Okay, not wholly classical, but
I would say right now the situation is that we have these truncations and as a sort of a sanity check, but it indeed was more much richer than expected, is that this limiting situation is giving you back the geometry that you started with. But that's just because the Dirac operator does that for you. Now, what you would like to do is that at finer and finer levels, so larger and larger truncations, you want to add something to these truncations by replacing maybe this truncated Dirac operator by adding these correction terms, and it will change the way the structure will be. So the state space you're trying to describe will change, so the metric will change, but that's still waiting to be developed. So.
Okay, so not only taking the spectral truncation, but also some modifications coming from this, for example, interactions with these quantum fields, yes?
For instance, yeah, exactly, yeah.
I see. Okay, thank you very much.
Joe, go ahead.
Hello. There's something I would like to question I should have put at the beginning. When you make the spectral truncations, say with the Dirac spectrum, you immediately lose positivity for the matrix algebra. So how do you get it back? Because in an operator system, you start with any positive cone of a suitable type. But what do you do when you truncate? What's your positivity then?
It's actually the one induced, so it's actually compatible with the compression. So the compression is a unital completely positive map.
Okay, so you just anything that was positive before you compressed is still positive.
Yeah, and then it's of course nice that for Toeplitz matrices, this happens to be well, it's not a coincidence, but it's the positivity of the matrix.
Right. Okay.
And somehow this is of course an intriguing question: is that somehow you have a positive Toeplitz matrix, and then you know that came from a function which is actually positive, and that's another old problem, of course, that you're very familiar with. So that's a beautiful situation where you have these sort of old problems coming back, but that compression is in principle completely positive and also unital.
Okay, thanks.
Anybody else?
I have a question about certain operator system. First, I would like to thank you very much for your very wonderful talk. And second, my question is that for a compact Lie group or a compact topological group with given with its Haar measure, one may forms an operator system in the space consists of all continuous functions defined on the Lie group or topological group whose integral is vanish, whose integral over the group is equal to 0. First, is it a well-known example of an operator system? And second, how can one recover and characterize all abstract operator systems which arise in this way? Namely, as the space of all continuous functions on the compact groups whose integral is 0. Are there some invariant, for example, are there some classical interpretation for propagation number of this operator system or something else? Do you think that these questions can produce some research?
It's an interesting problem, but I'm wondering. So if you take such functions, what would you call positive?
Sorry?
What would you call positive then? Because you need a cone of positive elements, and you take continuous functions whose integral vanish. So somehow you have to balance, say, the positive and negative part. So I'm not wondering if you get actually an operator system, because the negative of the cone and the intersected with the cone should be 0. And I'm not sure if this will happen here, but maybe your cone is trivial. I don't know. So what do you have in mind for cone of positive elements in this?
To be honest, I didn't pay attention to the cone, but I just pay attention to the definition of operator system in the form that every mn of E should get a norm. For example, a representation of CG on some Hilbert space, and consider it as a closed subset of BH. But as you say, that the positive elements should have another interpretation, not identical to the usual one. Yes,
Yeah,
you're
yeah.
that the cones is not a trivial subject in this way.
Yeah, so it's something to figure out probably. Yeah, but I think that's somewhere where you have to look at whether that condition is satisfied. But okay, I would have to sit down maybe and take a look at it. But thanks.
Yes. Okay.
Okay.
Thank you.
Anybody else? If there are no other questions, let me make just a very random comment, if you will. I mean, it's not very deep, but this is what came to my mind when I was listening to your talk. Because you know Walter Hoppe-Galois theory, right? You remember that stuff. And at a certain moment, is simply by the nature of examples, which came immediately, like Podley spheres and so on, you are pushed beyond Hoppe-Galois theory to C-Galois theory, and you lose this multiplicative structure. So somehow, when you lose that sister algebra structure and you just have operator systems, for me, it rings the same bell, right? You want to consider examples which go beyond the happy cases where you can multiply. Yeah,
Exactly.
it's not a deep comment, but it just
No,
came to my mind.
it's a good point, because indeed that or immediately comes and enters right from Hoppe-Galois into, you find that only the coalgebra structure actually survives in a sense.
Exactly.
Yeah.
Yeah. Exactly.
Yeah.
Exactly.
No, it's a nice. Well, this is of course the nice territory, I think,
Yeah.
where you see these.
And then we can do amazingly much with C-Galois, which we can do with Hoppe-Galois. This is quite remarkable how much we can do. Of course, it's an order of magnitude more difficult to do things, but you can prove them, you can work with them. Okay,
Yeah.
if there are no further questions, let us thank Walter again. I have this animated clapping. Yes, thank you very much.
There you go.
And let me stop recording.